Section 3.2, day 1. Monday is a shortened schedule. You get to sleep in. I'm not sure where hour is on Monday. I would assume there is one, but not sure. Okay, shh. Okay, guys. Monday, it's on your Schoology calendar. Okay, there we go. But Monday we have a short quiz. It's just 2 problems. It's only on section 3.1. I don't remember who had it. Well, now at least we can see the screen. Oh. And I've enrolled you in Schoology, so. Okay. The week. This isn't going to take us long, so we already did a lot of this yesterday. I just kind of did it all. So we have a quick quiz on Monday, and it'll be work time on Monday, maybe an activity. I'm not sure. I'd like to have us draw some functions, but we'll see. Here's what we're going to look at today. How does you know if a derivative fails to exist? I've really talked about it, but we'll talk about it more. If a function, Riley, is differentiable, then that means you can approximate that with a line, but we'll talk about that. I can do derivatives on a calculator again. And we already talked about if a function is differentiable, it's continuous. We did all that. And then just one-sided derivatives. We'll talk a little bit about that. I doubt you'll see one-sided derivatives on the exam. Okay. Graphs of differentiable functions can be approximated by tangent lines at points where the derivative exists. So here is my curve. And if I draw a tangent line at some point on the curve, as long as I am close to this point, I can use the tangent line, like maybe over here, to approximate this particular y value on the curve. Because it's usually easy to evaluate a linear equation than some fancy whatever that is, whatever function that might be. It's also the way your calculators work. There is no sine and cosine or tangent table in the calculator. It uses the calculus, and it does derivatives and stuff like that, and it actually approximates everything on those curves with tiny little tangent lines, so small you can't see them. That's how tiny they are. So you're really close to that point. So it's kind of interesting where the calculus is used. E to the x, there's no little table in there. It tells the calculator how to do e to the x. Okay, so where do derivatives fail to exist? This is probably the most important piece of this whole thing. A function will not have a derivative where the slope of the secant lines fails to approach a limit as x approaches a. So if we took the absolute value function right here, and you try to zoom in on it, and we will do one like that. The slope on this side is what? 1, and the slope on this side is -1. So how close can you get to this corner here? You can get as close as you want. We'll actually zoom in on one graph and show you. It doesn't matter. I always get the same picture. You should have seen that in the lab, right? When you zoomed in on it. Okay. When you say a function has a limit at a certain point, it has to be a single number. I've got 2 numbers, which one is which. This is like being in reverse. You're backing the car out of the garage, and then you shifted it forward, but you didn't bother to stop. You can't have an abrupt change. Don't do that. It's not a good thing. So sharp corners, that's one of the places, like the absolute value function. Now, to me, a cusp and a sharp corner, there's no difference. So this is a cusp. It's still an abrupt change. Your slope of your tangent line here and your slope of your tangent line there. So no abrupt changes. In this book, they put sharp corners and cusps in the same group. Okay. Yeah. No, because there's not. It's if you were to zoom in on the top of this, could you get it to look like a line? Yes. It's when you can't get it to look like a line, no matter how many times you zoom. Okay, vertical tangents. Now, what they're going to do on the exam is they'll give you probably a multiple choice question with a function that's discontinuous and some places where it's not differentiable. They might say which points are not continu or which points are continuous but not differentiable. And you're going to look at a picture, just like we're doing right now. Okay, Noah? Okay. What you guys know what the cube root looks like? Well, it looks like a square root, but square roots only have the domain x is greater than or equal to 0. Okay, Riley? Brian? And the cube root is this side. And this has a vertical tangent. These are the ones I tend to forget about. And you should have done one of these on your lab as well. And if you zoomed in or you did the calculator and it said the slope was 100, you know what that means? That means if you go over 1 foot, you're going to go up 100 feet. I'm going to be off my board. It's going to look vertical. The calculator has limitations. The calculator can't do a vertical line. That's the problem. So that's why it gives you a value. It's getting really big. You may not think 100 is big, but it's basically a vertical line. And the other place where we have problems with derivatives is where we have a discontinuity. We can't have any breaks in the graph. She's at it. Okay, so any kind of jump, vertical asymptote, hole, should put a hole there. So there's no breaks in the graph. So, and that's all there is. You're just looking for anytime the slope changes abruptly, sharp corners or cusps. Anytime you have a vertical tangent, or any time you have a break in the graph. Those places you can't take derivatives. That's it. That's all there is. Okay, so let's look at this function. Now I am going to use my inspire because it comes in there nice, a little bit nicer. If you have questions, ask. Yeah, are those a lot of Pardon? Yes, they are. Yes, they are. Yes, they are. They were not allowed on the IB or the ACT. Okay. The thing I don't like about this software is I can't make it smaller so I can look and see what I've got. Yes, the 89 is allowed. But the 89 is not as friendly. If you learn how to use it, that's fine. Okay, so we're going to graph this x minus, absolute value of x minus 2 plus 3. Now, to get absolute value on this thing, I have to type ABS. It's the same on, you have to get it in the pull-down menu on the 84, but it's the same. So it's x minus 2. And we should know what this looks like, right? Don't need to do a graphing calculator, but we will. And there it is. Okay, I want to zoom in on it. So I'm going to press menu, and I'm going to zoom, and I'm going to zoom in, and I want to center it right there. Will it ever be a straight line? Look at your numbers, they're pretty small there. You can keep zooming in all you want. Did you do that? Eventually it's going to fail. Look how close to 2 I am. I can't get it. No matter how many times I zoom, I can't get it to be a straight line. Okay, so that's not differentiable. That's all you have to do. Worked the last class, but now it's not working. did a different function. That's okay, it's the same. Okay, no matter how much I zoom in on it, you can't do this. Okay, there are theorems, and you need to know this. All polynomials are continuous and differentiable. So the key word here is differentiable. So you can take the derivative of a polynomial. Question is, do you know what a polynomial is? No. Poly means many, so it's got many terms, and n is a whole number. So x squared, for instance, x cubed, those are polynomials. That's actually a monomial. It only has one term, but you could combine it with other ones. So I know for a fact that polynomials are always differentiable. Rational functions are also always differentiable. Okay, the numerator and the denominators are polynomials. There's only one problem with a rational function. The denominator can't equal what? 0. How about your trig functions? Every place in the domain. Sine function looks like this, so does the cosine. So sine of x, cosine of x. The only one you have problems with is tangent, but as long as you stay in the domain, you're okay. Remember what the domain is for this? Tangent is going to be restricted to be between minus pi over 2 and pi over 2. So it's not differentiable at those vertical asymptotes, but everywhere inside. How about exponential functions? Oh, exponential logs. Let's start with the exponential. Remember what exponential functions look like? Noah? See? They look like this. Now, I'm going to tell you right now, this exam is heavy with exponential functions, especially e to the x. And it's heavy with logs, especially natural log of x. So we have to know these. Do you remember how to get the log function? To reflect over y equals x? So it looks like this. Now, the exponential function is differentiable everywhere. But the log functions are only differentiable for x what? Greater than 0. That's all. And this is everywhere. So you have to look at your domain. So on the exam, you could say, if they asked you to show something, you could say, well, polynomials are always differentiable everywhere. It just depends on the context. Okay. Local linearity. Differentiable functions are locally linear if we can zoom in far enough and the curve looks like a straight line. So when you did that lab, you zoomed in on this curve and you made it go got really close to 2 points, and the actual curve looked like a line, didn't it? That's what you mean by local linearity. So that's if you zoom in. Okay, should have noticed that in the derivative lab. That was really the main idea there. So it's actually very nice. If you stay close enough to wherever that point is, you can use that line to approximate your function. So what about this one? What does this graph look like? Well, I'm going to do my absolute value function. Set it at 0, and what does the plus 1 do? Shifts it up 1. And no matter how much you zoom here, we just did the other one. We don't have to do this again. Can you ever get to make it look like a straight line? No. The slope on the right side is 1. The slope on the left side is -1. I can't get those to ever be the same. It would have to go through 0, and they're not. They always stay the same then. So it's not differentiable at 0. And I can just abbreviate that. And you know what you would say? Sharp corner. That would be okay. They're not going to be that fussy about that. You'd say the derivative from the left doesn't equal the derivative from the right. Okay, any problem with that? So it's really just those things. did I just do? Okay, now, do we need to go over the derivative on the calculator again? Okay, we will do that. If you want to do it with me, get a calculator out. I've got a sum in my drawer. Yes. Oh, that's a good question. We talked about that in the other class. We have a first semester final, but we do not have a second semester final. Yeah. Okay. So I have already put my function in here because I did in the last class, and I'm in the classic mode. Now, it's asking me to find the derivative at -3, 0, and 2. I will put my function into y1 because then I can use that. And so we're going to do n derived, and it's going to be y1, comma x, comma whatever a value that is. Now I got to get this back up. Okay, so do you remember where n derive is? Math 8. I'm going to move this over here. So I'm going to quit. I'm going to type math, and it's 8. On the Inspire, you type in n derive, or you actually use a little derivative symbol. Now, remember how to get y1? It's bars. It's a y variable. It's a function, and I want the first one. You really want to put your functions into the y values, because otherwise you're going to have problems with parentheses. At least I do. Math 8. And then you have to have commas. Except I'm trying to remember where the comma is on this thing. Thank you. I get used to one calculator and switch. Then you have to do it with respect to x, comma, whoops, comma. And then we need to do this at -3. Then close your parentheses, and you press enter. No, I like the pretty print. I have to do it this way because most everybody has this. So let me do one more, and then I'll switch to pretty print. Let's put in 0. Now, I don't want to type that again. If you have the new operating system, you can just arrow up, or you can do second enter, which is actually easiest. And I want to put a 0 in there. I don't think it works if I put a -0 in there. I think it gives me an error. So I'm just going to get rid of the minus, and there it is. So if you have to do a bunch of points, you can just do second enter. Now I'm going to change my mode. I'll fix this one here. And I want to be back in math print. Okay, cleared everything out. Wasn't happy about that, but okay. It's math. Well, you know what? If you have that pretty print, you just go alpha, window, and there's n derive. It's a shortcut. I don't think it's that much shorter. And this looks like our derivative operator. This is only if you have the 84 with the new operating system. Yeah, you have to have the new operating system. I can get it to you. I can get it for you. All we need is one that has one on there. Okay, this is your x. That's the same x that we have up in n derive. So it's x. And then I need my function. And guess what? There is a shortcut for that too. It's alpha trace. And you can pick up y1 right there. If you don't have it, I can get it for you. And we're going to do this at -3. I have to have it with somebody's. Okay. Yeah, we just did it. Let me go back to classic. We just did it. Okay, so now let's see if I can. I don't know why I can't get to that. So I'm going to bring up my calculator again. I'm going to switch it back to classic print. There it is. And when I do that, I'm going to lose my screen. Okay, so I got to go back to mode. I've got it on the smartboard. Okay, and we want to go to classic. There you go. Okay, so you go to math. You're in the old system. You have to go to 8. I can arrow down or I can just type 8. I prefer to type 8. There it is, end drive. Press enter. And then you have to get your y values. So you press bars. And we're going to do y variables. y1, comma, x, comma. Let's put 2 in this time. There's 2. You have to put it in y equals. Make sure you put your function in y equals. Okay, you ready for the last bit? That's all there is. Okay, you guys? Well, there's a little bit left. One-sided derivatives, you can still have a function differentiable at a point from one side. For instance, if I have y equals the square root of x, remember what that looks like? It looks like this. Remember, this is right continuous? You can find, I don't know if you can find the derivative there. I don't think you can. But you could try to find the derivative from the right because the domain doesn't include the negatives. So that's all you're going to do is let h go to 0. This is coming in from the right side, and this is coming in from the left side. So you could have a one-sided limit. They're not going to put that on the exam either. So I warn you when it's not going to be there. If it's there, I'd be shocked. Now, we talked about this yesterday, part 5. If you have a differentiable function, that means it has to be continuous. So when, on the exam, they're going to say, you have a differentiable function, so then you're going to say, oh, I know it's continuous. That the derivative exists, that you can find the derivative. If you can find the derivative, the graph has to be continuous, doesn't it? Yes. They will not tell you the graph's continuous. They'll tell you it's differentiable. Question? Jack? I'm not going to listen to music. Okay. Just because you have a continuous function doesn't mean it's differentiable. What if you have a continuous function? Is it differentiable? Absolute value. So we did this yesterday. This is a review. Now, intermediate value theorem is also review. Now, your derivative is a function. And guess what? You think you can do a second derivative? A derivative of a derivative? And they're going to have special meaning. We call it the second derivative. So, if f of a is negative 2 and f of b is positive 10, what has to be true about my y values? They have to, assuming f of x is continuous, has to be continuous, then my y values, we're going to have to hit, I don't want equal to. They're going to have to hit every value between negative 2 and 10. So your temperature outside, if it was 2 below and it gets to be 10 degrees above, it had to be 2 degrees sometime, or in particular 0. Well, it's the same is true for derivatives. If I tell you that the derivative at a is equal to negative 2 and the derivative at b is equal to positive 10, then the derivative, which it would have to be continuous, has to be between negative 2 and 10. So it's no big deal. It's just the intermediate value theorem because the derivative is a function. For this to happen, f of x had to be continuous. Derivative is the slope of the tangent line. It's the slope of the tangent line. Implies. that f of x is continuous. And I think that's all we have. There it is. If f prime takes on all values, then f had to be continuous. It's saying the derivative exists everywhere. So now the question is, when are we doing the shortcuts? Monday we have a work day with a little short quiz. Tuesday you have college fair for the juniors. So that's a work day on Tuesday. And Wednesday is when we start the shortcuts. For seniors. Yeah, seniors, I'll miss some of you. Tuesday. Not yet. The quiz is on the definition of a derivative. Okay, shh, you guys. You got to know the definition of a derivative because they're going to come up with problems like 57 through 60 in the book, just like those. And you're not going to do the limits. You're going to say, oh, that's the derivative of, and you're going to find the derivative using the shortcuts. They could possibly ask you to do a derivative using the definition. They could do that. I haven't seen it since the 80s. So I don't know. Okay, so what did we do today? What did we do today? We basically looked at where derivatives don't exist. Anytime you have an abrupt change in your graph or a hole in your graph, any kind of break in a vertical tangent. And that's in your book. It's listed in your book quite nicely. I think it's on page 141. It could be wrong. That's not 141. It's, oh, it might be. It is 141. When is a function not differentiable at a point? Read the book. This book isn't too bad to read. Okay. Are there more questions from 3.1? Of course, if you haven't done it, you can't ask me a question. Otherwise, you have about 20 minutes to do some work. Are you going to ask me questions or do work? Can I what? Yeah. Got one? Not much there, really. Mm-hmm. Unless you want me to go to board and do problems.